Alright, so the next thing we're going to do is a von Neumann stability analysis on this equation that we derived earlier. And to do that, we're going to need to keep in mind Euler's formula, which I've written here. And then also, here are the x and t definitions that we also derived in relation to this equation. So for this stability analysis, we're going to be using this solution for the temperature. And we're going to be using that, and plugging it into here, and then figuring out some bounds on what R can be for the stability analysis. So first thing we're going to do is we're going to start using this to plug values in here. And we're going to try to plug them in terms of t at j at n. So let's first solve this for that. So we'll have that the value of t at j at n is equal to, so e to the I, k. So now x in this case is j times delta x. So j is just j. So times j delta x, and times e to the negative alpha of k squared times the time, which is n times delta t. Alright, so this is t at j at n. So also in here we're going to need t at j plus 1 n. So we can do that next. So that's important. So now we have t at j plus 1 at n. So that is equal to e. So to that I, okay, so this time x is j plus 1, so we'll have j plus 1 delta x times e to the negative alpha, and n's the same as it was up here, so this term is the same. Alright, so then we want to put this in terms of that, so we've got t at j plus 1 n. Alright, so then we're going to have t at j comma n times some value, so these will cancel out, and then this is, we factor into the j plus 1, and so when we factor into the j, that's this, and then we'll have another 1 times 1, so that would be times e to the I k delta x. So if you multiply this, this by tjn, so we multiply this by this term, we would end up with this term here. So that's t at j plus 1 at n. So now we also need t at j minus 1, which is similar. So t at j minus 1 at n is equal to e to the I k of j minus 1 delta x times e to the negative alpha k squared and delta t. And same thing, we can put it in terms of t at j at n. So t at j minus 1 at n is equal to t at j at n times, so it's going to be e to the negative I k delta x. Because again, if you multiply this, or this times t at j n, which is this, we'll get this right here. So that works out, so this is our other value. And then we can plug those three things into our equation up here. So we've got t at j at n plus 1 is equal to r times t at j plus 1. So that's this. So we've got t at j at n of e to the I k delta x. We've got plus 1 minus 2r times at j at n plus r. So then r times j minus 1, that's this one. So we've got t at j at n e to the negative I k delta x. Alright, so then you can see we can factor out this t at j at n. So we'll do that. We got t at j at n plus 1 is equal to t at j at n times. Alright, so then we've got this e to the I k delta x, and then I'm going to put this next to this term so we can see it better. So that's e to the negative I k delta x, and then we need this one as well, so that's plus 1 minus 2r. Oh, and then these need r's as well. So we got r here and here. Alright. So that's that. So now here is where we can take into account Euler's formula. So Euler's formula is e to the ix equals cosine of x plus I times sine of x. And that can be rearranged for the form e to the ix plus e to the negative ix is equal to 2 cosine x. So this form right here is similar to what we have right here. We've got e to the ik delta x plus e to the negative ik delta x. So we can use that substitution in here. So we've got t at j at n plus 1 equal to t at j at n times, so then this is r times 2 times cosine of k delta x. Because in this case, this k delta x is the generic x that we've got in this formula here. Alright, so then plus 1 minus 2r. Alright, so now we want to combine this a little bit. So again, t at j at n plus 1 plus t at j at n. And then we have, so we'll have 1 minus, I'm just going to write everything out, so 2r plus 2r cosine k delta x. So then this one we can factor out the 2r. So then we got t j n plus 1 is equal to t at j n times 1 minus 2r, so then plus 2r, and then we'll have negative 1 plus cosine of k delta x. So this is how we would factor that out. Alright, so at this point, we can see that for this to be stable, we need this value here to be less than 1. And that's because if it's going to be greater than 1, then this has the possibility to go to infinity, which is not stable, and we're performing a stability analysis, so that is not ideal. So we're going to take this term in here and set it equal, hold up, let me get the lights. Alright, so at this point we're going to set this term less than 1, actually it should be less than or equal to 1, so because if we multiply by this by 1, it's not going to go to infinity, so it's fine if it's equal to 1 as well. So, and it's going to be the absolute value of this is less than or equal to 1, so that would mean that it could be negative 1 on one side, like between negative 1 and positive 1, so that's how we're going to write it. So we're going to have negative 1 is less than or equal to 1 plus 2r times negative 1 plus cosine of k delta x, which is less than or equal to 1. Alright, so then what we want to do is we're going to start solving for r, because r is the value that we want to put constraints on. So first thing we do, subtract the 1, so we've got negative 2 is less than or equal to 2r times negative 1 plus cosine k delta x, which is less than or equal to 0. Alright, so now we can look at this. We know cosine is always going to be between negative 1 and positive 1. And so we also know that r is always going to be positive, just based on, the components of r. Everything's always going to be positive. R is always going to be positive. So since cosine is always going to be, between negative 1 and 1, and then we subtract 1 from that value, this term here is always going to be less than or equal to 0. So this side of this inequality is always true no matter what, so we don't really have to worry about it, and we can just focus on this negative 2 side. Alright, so now, so at this point, we can do the next step where we divide by 2. We got that negative 1 is less than or equal to r times negative 1 plus cosine k delta x. Alright, and now we can divide by this. So then we'll get that negative 1 over negative 1 plus cosine k delta x is less than or equal to r. Okay. I'm going to move up here. So at this point, we're going to multiply everything by negative 1 so that we don't have all these weird negatives in here. So we're going to have that 1 over 1 minus cosine of k delta x. And since we're multiplying by negative, it flips the sign, so it's going to be greater than or equal to r. So we just multiply by everything by 1, and we get this. So at this point, we're kind of done simplifying. We've solved for r, which is great. We just need to now figure out what the bounds are. So to figure out what the bounds are, we need to know what the bounds on this value are, because we're solving this for any k delta x. We haven't specified. So the bounds on this. So cosine, as we discussed earlier, cosine is always going to be between negative 1 and positive 1. So those are going to be the two bounds that we're using. So first, we'll have if cosine is negative 1, so that's going to be 1 over 1 minus negative 1 is greater than or equal to r. And then 1 minus negative 1 is 2, so that means that 1/2 must be greater than or equal to r. And then the other, the upper bound on this is going to be if cosine was 1, so we'll have 1 over 1 minus 1 is greater than or equal to r. 1 minus 1 is 0. 1 divided by 0 is infinity. So that means that infinity is greater than or equal to r. So then, if we look at these two things, r is always less than infinity, and r always has to be less than 1/2. Well, anything that's less than 1/2 is also going to be less than 1 infinity. So this is the main constraint that we're going to be looking at, because it's a tighter, more strict constraint than infinity. So there we have values of r that will contribute to a stable solution.